Quantum mechanics begins with a quietly uncomfortable idea. The world may not be quite as solid, settled, or obvious as it appears. Not in the sense that reality is fake, or that the universe is playing tricks for dramatic effect, although it does sometimes seem to enjoy a little theatre, but in the deeper sense that the rules beneath matter, light, and measurement are far stranger than everyday experience suggests. At ordinary scales, reality behaves politely. A cup stays on the table, a shadow follows the lamp, a door is either open or closed unless it's a very old door, in which case it may complain somewhere in between. But at the scale of atoms, electrons, photons, and tiny packets of energy, nature becomes more subtle. Possibility matters, observation matters, and the old idea of a perfectly definite world waiting quietly in the background begins to soften. Welcome to the Late Lab. It's wonderful to have you here. Before tonight's little journey begins, take a moment to settle in. Maybe you're watching from a quiet room with the lights low, a sofa that has quietly claimed you for the evening, or somewhere in the world where the day is only just beginning to soften around the edges. Wherever you are, I hope you're warm, comfortable, and ready to let your thoughts drift toward one of the strangest ideas science has ever uncovered. If you enjoy these calm explorations and would like more slow, thoughtful science to unwind with, a like and subscribe helps this little corner of the internet keep humming along. And if you're already subscribed, thank you. Truly, your support helps the Late Lab keep the lights dim, the questions large, and the experiments safely contained in the imagination, which is usually the best place for them at this hour. Tonight's topic is quantum mechanics, the theory that changed the meaning of reality. Not just because it made physics more complicated, although it certainly did that with impressive commitment, but because it forced science to ask what can actually be known about the world before it is measured. For centuries, reality seemed fairly straightforward. Objects had positions, events had causes. The moon was there whether anyone looked at it or not, which is polite of it. But in the early 20th century, physicists discovered that matter, light, energy, and measurement itself behaved in ways that did not fit the old picture. Particles could act like waves. Waves could arrive as particles. Atoms seemed to obey rules written in probability rather than certainty. And the act of observation was no longer a passive glance from the outside, but part of the story itself. So let's begin gently, with the world before quantum mechanics, when reality still seemed solid, predictable, and reassuringly well behaved. Before quantum mechanics arrived, reality had a certain comforting firmness to it. The world seemed to be made of objects with places, weights, speeds, paths, and causes. A stone thrown through the air followed a curve. A planet moved around the sun. A clock ticked forward. A cannonball once fired did not suddenly become a mist of possible cannonballs, which was considerate of it, especially for anyone standing nearby. This older picture of nature did not appear all at once. It was built slowly over centuries by people trying to understand motion, matter, light, and force with increasing precision. Galileo Galilei helped loosen the old medieval view of motion by studying falling bodies, rolling objects, and the behavior of projectiles. He showed that nature could be questioned by experiment, not only by inherited authority. The world in his hands began to look less like a collection of mysterious qualities and more like something that could be measured. Then came Isaac Newton, who gave this measured world a grand and powerful structure. In the late 17th century, Newton described motion using laws that connected force, mass, and acceleration. He also described universal gravitation, the idea that the same kind of attraction pulling an apple toward Earth also helps hold the moon in orbit. This was a breathtaking simplification. The heavens and the ground beneath your feet were no longer separate kingdoms with separate rules. They were part of one physical system. In Newtonian mechanics, an object has a definite position and a definite motion. If a planet is moving through space, it is somewhere in particular, travelling in a particular direction, with a particular speed. If all the relevant forces are known, its future motion can be calculated. A falling apple does not have to consult a committee of possible futures before deciding where to land. It simply follows the laws of motion. This made reality feel, at least in principle, knowable. Difficult, certainly. Vast, complicated, and occasionally rather inconvenient, yes, but not fundamentally hidden. If a person did not know where a comet would be next year, the problem seemed to be lack of information or lack of calculation, not a deep uncertainty built into nature itself. The universe looked like a grand machine, and science became the art of learning how its gears turned. René Descartes had earlier helped shape another important part of this mechanical picture. He imagined nature as something extended in space, made of matter in motion, governed by rules that could be understood through reason. Even when later science moved beyond many of Descartes' specific ideas, the dream of a rational, orderly, mechanical universe remained powerful. Matter had location, motion had cause. Reality, in the broad classical view, existed clearly whether anyone was watching or not. This confidence reached one of its most famous forms in the idea associated with Pierre-Simon Laplace. Laplace imagined that if an intelligence knew the position and motion of every particle in the universe, and understood all the forces acting on them, then it could calculate everything. The future, the past, every event that would ever unfold. This imagined intelligence is often called Laplace's demon, though it is less a horned creature and more a terrifyingly gifted accountant of the cosmos. The point of Laplace's demon was not that such a being actually existed. It was a symbol of determinism. In this view, the present state of the universe fully determines what comes next. Every future event is already contained in the exact arrangement of the present, like a vast clock whose future ticks are fixed by the position of every wheel. Chance, in this older picture, often meant human ignorance. A coin toss looked random because the motion was too complicated to track, not because nature itself was undecided. By the 19th century, this confidence only grew. James Clerk Maxwell produced one of the great unifications in the history of physics by showing that electricity and magnetism were different aspects of a single electromagnetic field. His equations described how changing electric fields create magnetic fields, and changing magnetic fields create electric fields. Out of this elegant structure came a remarkable conclusion. Light itself is an electromagnetic wave. This was not a small detail. Maxwell had connected the glow of a candle, the spark of electricity, the pull of a magnet, and the invisible waves that would later carry radio signals into one framework. It was one of those moments in science when separate pieces of reality suddenly turn out to be pages from the same book. A very mathematical book, admittedly, and not one to read casually over breakfast, but still a single book. By the late 19th century, physics seemed impressively complete. Newton had given laws for motion and gravity. Maxwell had explained electromagnetism and light. Thermodynamics described heat, engines, energy, and entropy. Classical physics seemed able to explain planets, pendulums, waves, machines, pressure, temperature, and the behavior of matter in bulk. The world appeared lawful from the motion of stars to the working of steam engines. And beneath this confidence sat a simple assumption. Reality was definite. Objects had properties whether or not anyone measured them. Measurement revealed what was already there. A planet did not wait to be observed before having an orbit. A stone did not wait to be examined before having a position. Light, in Maxwell's theory, spread as a wave through space according to precise rules. Matter moved as matter. Waves behaved as waves. The categories seemed tidy enough. This older worldview is important because quantum mechanics did not merely add a few strange facts to science. It challenged the meaning of those categories. Before quantum mechanics, it was natural to think of reality as a clear inventory of things and properties. Particles here, waves there, forces acting between them, courses leading smoothly to effects. The observer stood outside the system looking in, like someone checking the time on a clock without changing the clock by glancing at it. But small puzzles were beginning to gather at the edges. Heated objects gave off light in patterns that classical physics could not properly explain. Atoms emitted sharp spectral lines instead of every possible colour. Matter was stable, even though older electromagnetic theory suggested that electrons moving around atomic nuclei should lose energy and collapse inward. Light behaved like a wave in some experiments, yet would soon seem to arrive in packets in others. These were not enormous cracks at first. They were subtle, technical, and easy to underestimate. To many physicists, they looked like loose threads in an otherwise strong fabric. But once pulled, those threads began to unravel the old certainty. The world of atoms and light would not behave like a tiny version of the everyday world. It would not be a miniature clockwork, politely shrinking classical physics down to microscopic size. The comfortable world before quantum mechanics was not foolish. It was powerful, elegant, and still works beautifully for countless ordinary situations. Bridges, planets, engines, falling objects, and much of daily life can still be understood through classical ideas. But beneath that dependable surface, nature had been keeping a quieter set of rules. And when physicists finally noticed them, reality would never mean quite the same thing again. The first cracks in classical certainty did not arrive with thunder. They arrived as small, awkward problems in the laboratory, the kind of problems that look harmless at first and then quietly refuse to go away. By the late 19th century, physics looked confident from a distance. Newton's mechanics explained motion. Maxwell's electromagnetic theory explained light. Thermodynamics explained heat and energy with impressive practical success. Steam engines, telescopes, clocks, and electrical machines all seemed to belong to one orderly universe. But the trouble was hiding in places where matter and light met very closely. It appeared in the colours given off by hot objects. It appeared in the sharp lines of light emitted by atoms. It appeared in the simple fact that atoms were stable at all. These were not vague mysteries. They were measurable, repeatable, and stubborn. That made them more dangerous to the old world view than a dramatic philosophical argument, because nature was not debating. Nature was just producing results. One of the most important puzzles was blackbody radiation. A blackbody is an ideal object that absorbs all light falling on it, and then emits radiation depending on its temperature. A perfect blackbody is an idealization, but the idea is closely related to familiar things. A piece of iron placed in a fire begins to glow dull red. Make it hotter, and it glows brighter, then orange, then yellowish white. Warm embers shine softly in the dark. The heated filament of an old light bulb glows because its temperature makes it radiate visible light. Even objects that do not visibly glow still emit infrared radiation, which is why a warm hand can be seen by a thermal camera. Classical physics could describe some of this behaviour, but not all of it. The problem became especially sharp when physicists tried to calculate exactly how much radiation a hot object should emit at each frequency. The older theory worked reasonably well for lower frequencies, but at higher frequencies it went badly wrong. It predicted that a heated object should emit an unlimited amount of energy at ultraviolet and even higher frequencies. In other words, the mathematics suggested that hot objects should pour out absurd amounts of high-frequency radiation. This failure became known as the ultraviolet catastrophe. It is a wonderfully dramatic name for what was, in practice, a deeply embarrassing calculation. The universe, thankfully, did not behave that way. Ovens did not fill the room with impossible floods of ultraviolet light. Fireplace pokers did not become physics disasters with handles. The measured radiation curve rose, reached a peak, and then fell away at higher frequencies. Experiment was calm. Classical theory was the one waving its arms. In 1900, Max Planck found a way to solve the problem. Planck was not trying to announce that reality was stranger than anyone had imagined. He was trying to make the mathematics fit the observed radiation. His solution was to assume that the energy exchange between matter and light could not take just any value. Instead, energy had to be emitted or absorbed in small discrete amounts. These small packets became known as quanta. This was a quiet but enormous step. Classical physics had usually treated energy as something continuous, like water poured from a jug. You could pour a little, then a little less, then an even tinier amount, at least in principle. Planck's idea suggested that, at the deepest level, energy exchange might be more like coins than flowing water. You could pay in fixed units, but not in any amount whatsoever. Nature, it seemed, might keep a tiny accounting system of its own, and unlike most accounting systems, this one would change physics forever. Planck introduced a constant to describe the size of these energy packets. This became Planck's constant, one of the central numbers in quantum theory. It is extraordinarily small, which is why quantum effects are usually hidden in everyday life. On human scales, energy often looks smooth and continuous, because the individual steps are far too tiny to notice. But at the scale of atoms, electrons and light, those steps become essential. Black body radiation was not the only warning sign. Atomic spectra also troubled classical thinking. When atoms of a gas are excited, they do not emit a smooth rainbow of every possible colour. Instead, they emit sharp spectral lines, specific colours corresponding to specific energies. Hydrogen, for example, produces a distinctive pattern of lines. This suggested that atoms could only gain or lose energy in particular amounts. It was another clue that nature was not behaving continuously at small scales. Then there was the problem of atomic stability. By the old picture, electrons moving around an atomic nucleus should emit radiation, lose energy, and spiral inward. If that were true, atoms would collapse almost instantly. Ordinary matter would not be stable. Tables, stars, and people would be having a very short and disappointing career. Yet atoms plainly do exist, and matter holds together. Classical physics could not fully explain why. These problems were the first real openings through which quantum mechanics entered. It did not begin as a grand attempt to make reality mysterious. It began because experiments were too precise to ignore and too strange to fit the old rules. Planck's energy quanta were introduced as a practical solution, almost reluctantly. But once the idea existed, it could not be politely put back where it came from. The meaning of reality had not changed completely yet. But the old certainty had been disturbed. Energy might not be continuous. Atoms might not obey ordinary mechanical pictures. Light and matter might be governed by rules that only became visible when nature was examined at its smallest scales. The clockwork universe was still ticking, but somewhere deep inside it, something had begun to click in a very different way. Light had already been given a beautiful classical identity before quantum mechanics disturbed it. In James Clerk Maxwell's electromagnetic theory, light was a wave, a self-sustaining ripple of electric and magnetic fields moving through space. This picture explained reflection, refraction, interference, diffraction, and the colours of the visible world with extraordinary elegance. Light spread, bent, overlapped, and shimmered exactly as a wave should. It was one of classical physics' greatest triumphs. Then the photoelectric effect quietly made things awkward. The photoelectric effect occurs when light strikes the surface of a metal and causes electrons to be released. In itself, that may not sound especially strange. If light carries energy, and electrons are held inside a metal, then perhaps enough light should shake some electrons loose. A bright beam, in the older wave picture, ought to deliver more energy than a dim beam. So it seemed reasonable to expect that intense light, whatever its colour, should eventually push electrons out if it was strong enough or shone for long enough. But experiments said otherwise. Philipp Lenard, a German physicist, studied the photoelectric effect in detail around the turn of the 20th century. His work showed that the release of electrons depended in a very specific way on the frequency of the light. Frequency means how rapidly the light wave oscillates, and in visible light it corresponds roughly to colour. Red light has a lower frequency than violet light. Ultraviolet light has a higher frequency still, beyond the violet end of the visible spectrum. The troubling result was that low-frequency light could fail to release electrons no matter how bright it was. A powerful red light might shine on the metal and produce nothing. No electrons, no delayed escape, no tiny metallic sigh of cooperation. But a faint beam of higher frequency light could release electrons almost immediately. The brightness affected how many electrons were released, but the frequency determined whether they could be released at all. This did not fit comfortably with classical wave theory. If light energy were spread smoothly across a wave, then a brighter low-frequency beam should eventually supply enough energy to free electrons. The electrons might take a little time to absorb that energy, like someone saving coins slowly for a train ticket. But that delay was not observed in the expected way. Instead, if the frequency was high enough, electrons emerged immediately. If the frequency was too low, they did not emerge at all, however intense the light became. In 1905, Albert Einstein offered an explanation that pushed Max Planck's quantum idea into a much bolder place. Planck had introduced energy quanta to explain blackbody radiation, treating them at first as a kind of mathematical step needed to make the calculation work. Einstein went further. He proposed that light itself could behave as if it came in discrete packets of energy. Later, these packets would be called photons. In Einstein's explanation, each photon carries an amount of energy determined by its frequency. Higher frequency light consists of photons with more energy. Lower frequency light consists of photons with less energy. An electron in a metal needs a certain minimum amount of energy to escape, called the work function of the metal. If a single photon does not have enough energy, the electron stays put. Making the light brighter simply sends more low-energy photons, but each one is still individually too weak to free the electron. This made the photoelectric effect suddenly understandable. High-frequency light could eject electrons because each photon carried enough energy. Low-frequency light could not, because each photon fell below the threshold. Brightness controlled the number of photons arriving, not the energy of each photon. A brighter beam was like sending more coins, but if each coin was the wrong value, the machine still refused to open. Nature can be surprisingly strict about exact payment. Einstein's idea was revolutionary because it challenged the simple belief that light was only a wave. Light still behaved like a wave in many experiments. It produced interference and diffraction. It spread and overlapped. Maxwell's theory was not simply thrown away, but now light also seemed to arrive in particle-like packets, interacting with matter one photon at a time. This was one of the first clear signs that the categories of classical reality were beginning to blur. A wave was supposed to be spread out. A particle was supposed to be localized. Light appeared to be both, depending on how it was tested. It was not that scientists were merely confused about which label to use. The experiments themselves forced the discomfort. Light behaved in wave-like ways when wave-like behavior was measured, and in particle-like ways when particle-like exchanges of energy were measured. Einstein received the 1921 Nobel Prize in Physics for his explanation of the photoelectric effect. That detail often surprises people, because Einstein is so strongly associated with special relativity and general relativity. Yet the Nobel Committee recognized the photoelectric effect because it gave powerful evidence for the quantum nature of light. It also helped open the door to modern quantum theory, even though Einstein himself would later become deeply uneasy with some of the theory's stranger implications. The photoelectric effect changed more than the science of light. It changed the confidence that reality could be divided neatly into familiar kinds of things. Light was no longer simply a wave moving through space, nor simply a stream of tiny particles in the old mechanical sense. It became something deeper, something whose behavior depended on the kind of question nature was being asked. And that is where quantum mechanics began to alter the meaning of reality. Not by making the world unreal, but by showing that the old categories were too small, the universe was not waiting to fit comfortably inside human intuition. Light had kept its secret until the experiments became precise enough to ask properly. Then, quite calmly, it answered in packets. Atoms had always been a useful idea, but for a long time they were also rather shadowy. The word atom came from ancient Greek thinking, from the idea of something uncuttable, a smallest piece of matter beneath the visible world. By the 19th century, atoms had become much more than philosophy. Chemists used them to explain why elements combined in fixed ratios. Physicists used them to explain gases, heat, and pressure. Matter seemed to be made of tiny pieces, too small to see directly, but powerful enough to explain why the world had structure. And yet the atom itself was not easy to picture. By the early 20th century, scientists knew that atoms contained electrons, tiny negatively charged particles discovered by J.J. Thomson in 1897. Thomson proposed a model sometimes called the plum pudding model, where electrons were embedded inside a spread-out positive charge, a little like raisins in a pudding. It was not a bad attempt for the time. Science often advances through models that are wrong in interesting ways, which is better than being wrong in boring ways. Then Ernest Rutherford and his colleagues revealed that the atom was far stranger than Thomson's picture suggested. At the University of Manchester, Hans Geiger and Ernest Marsden carried out the famous gold foil experiment under Rutherford's direction. They fired alpha particles at an extremely thin sheet of gold and watched how the particles scattered. Alpha particles are positively charged particles emitted by certain radioactive materials, and in this experiment they acted like tiny probes fired into the hidden structure of matter. Most of the alpha particles passed straight through the gold foil. That was already interesting because it suggested that atoms were mostly empty space. But a small number bounced back at sharp angles, as if they had struck something extremely dense and positively charged. Rutherford later described his astonishment with the comparison of firing a shell at tissue paper and having it come back. The result made little sense if positive charge was spread gently throughout the atom. It made far more sense if almost all the atom's positive charge and mass were concentrated in a tiny central nucleus. This was a dramatic change in the picture of matter. The atom was not a soft pudding of charge. It was mostly empty space, with a tiny dense nucleus at its centre and electrons somewhere outside it. The nucleus was incredibly small compared with the atom as a whole. If an atom were enlarged to the size of a large cathedral, the nucleus would still be something like a speck near the middle. Almost everything that feels solid to the hand is, at the atomic level, structured emptiness held together by forces. This is one of those facts that sounds suspiciously like poetry, but is actually physics behaving with unnecessary elegance. Rutherford's nuclear atom was powerful, but it created a serious problem. If electrons were outside the nucleus, attracted by its positive charge, perhaps they orbited it rather like planets orbit the sun. This picture was tempting, and it still appears in simple drawings today. But according to classical electromagnetic theory, it should not work. An electron moving in a curved path is an accelerating electric charge. Accelerating electric charges should radiate electromagnetic energy. If an orbiting electron radiated energy, it would lose energy, spiral inward, and crash into the nucleus. That would be inconvenient. Not just mildly inconvenient like misplacing a teaspoon, but catastrophically inconvenient, like the entire material universe failing to exist. Classical physics predicted that atoms should be unstable. Electrons should not keep circling nuclei indefinitely. Ordinary matter should collapse. But ordinary matter plainly does not collapse. Tables remain table-shaped. Air stays breathable. Human beings manage to be made of atoms for more than a fraction of a second, which is always useful. Something was missing from the classical picture. The missing clue came from light. When atoms are heated or excited, they give off light in very specific patterns. If the light from glowing hydrogen gas is passed through a prism or a diffraction grating, it does not form a smooth, unbroken rainbow. Instead, it produces distinct spectral lines, particular colours at particular positions. Hydrogen has a visible pattern that includes red, blue-green, and violet lines. Other elements have their own patterns, like atomic fingerprints written in light. This mattered because each colour of light corresponds to a particular frequency and energy. If atoms emitted only certain colours, then atoms seemed able to release only certain amounts of energy. They were not radiating energy in a smooth, continuous range. They were making specific jumps. The atom was acting less like a tiny clockwork machine, and more like a strange musical instrument that could play only certain notes. In 1913, Niels Bohr proposed a model that made this mystery more understandable. Bohr took Rutherford's nuclear atom and added a bold quantum rule. Electrons, he suggested, could occupy only certain allowed orbits around the nucleus. While an electron remained in one of these allowed orbits, it did not radiate energy and spiral inward, even though classical theory said it should. The electron could move from one allowed energy level to another by absorbing or emitting a definite amount of energy. When it dropped to a lower energy level, it emitted light with a specific frequency. This helped explain the spectral lines of hydrogen. The lines were not random, they reflected electrons moving between specific energy levels. Each jump released a photon with a particular energy, and that energy appeared as a particular colour of light. The atom's light was not a continuous blur because the atom's energy levels were not continuous. They came in steps. Bohr's model was a breakthrough, especially for hydrogen, the simplest atom. It gave a physical reason for the sharp lines in hydrogen's spectrum and helped explain why atoms were stable. It also brought Planck's and Einstein's quantum ideas into the architecture of matter itself. Energy quanta were no longer just a trick for heated objects or a strange feature of light. They were becoming part of the atom's inner structure. But Bohr's model was not the final truth. It still pictured electrons as if they moved in neat orbits, and that picture would later be replaced by quantum mechanics. Electrons do not truly circle the nucleus like tiny planets around a tiny sun. The later theory would describe them through wavefunctions, orbitals, probabilities, and allowed quantum states. The familiar planetary image is useful as a stepping stone but misleading if taken too literally. Atoms are not miniature solar systems. The electron is not a small moon with a strict timetable and an impressive sense of punctuality. Still, Bohr's model was an essential bridge. It showed that the atom could not be understood by simply shrinking classical mechanics down to a smaller scale. New rules were needed. Electrons could not have just any energy. Light could not be emitted in just any amount. Stability itself depended on restrictions that had no comfortable place in older physics. This changed the meaning of solidity. A piece of metal, a glass of water, a human hand resting on a table, all feel continuous and firm. But their firmness depends on atomic structure, and atomic structure depends on quantum rules. The familiar surface of the world is produced by invisible patterns of charge, energy, and exclusion, arranged in ways that do not resemble ordinary objects moving through ordinary space. The atom became a mystery, because it revealed that reality's foundation was not built from tiny versions of familiar things. Matter was not made of little mechanical beads obeying miniature clockwork laws. Even the simplest atom required a new kind of order, one where energy came in steps. Light carried information about hidden transitions, and stability emerged from rules that classical physics could not explain. The world still looked solid. It still behaved dependably at human scales. But inside every ordinary object the old picture had failed. The atom had opened a door, and behind it was a reality far less obvious than the one the eye could see. The idea that light could behave like a particle was already strange enough. But quantum theory was not finished rearranging the furniture of reality. Once light had been given a double nature, both wave-like and particle-like, a new question appeared almost naturally. If waves of light could sometimes behave like particles, could particles of matter sometimes behave like waves? In 1924, Louis de Broglie proposed exactly that. He suggested that matter itself had wave-like properties, not just light, not just radiation. Actual particles, including electrons, might be associated with a wavelength. This was a bold idea, because electrons had been treated as small bits of matter with electric charge and mass. They were the little negative ingredients of atoms, not ripples. Giving them wave properties was like calmly suggesting that a marble might secretly have something in common with a note played on a violin. De Broglie's proposal connected a particle's motion with a wavelength. In simple terms, the faster and heavier something is, the shorter its associated wavelength becomes. For everyday objects, that wavelength is so unimaginably tiny that it has no visible effect. A football, a cup, or a person walking across a room technically has a de Broglie wavelength, but it is far too small to matter in ordinary life. Nobody walks through a doorway and diffracts noticeably into the hallway, which is probably for the best. For electrons, however, the situation is different. Electrons are extremely light, and at atomic scales their wave nature can become important. Their wavelengths can be comparable to the size of atoms and the spacing between atoms in crystals. That means electron waves are not just a mathematical curiosity. They can shape how electrons move, how atoms hold together, and why matter has stable patterns instead of collapsing into classical confusion. The crucial evidence came from diffraction. Diffraction is a wave behaviour. When water waves pass through a gap, they spread out. When sound bends around a doorway, that is also a kind of wave spreading. When light passes through narrow openings or around small obstacles, it can form interference patterns, where waves reinforce in some places and cancel in others. This is not how little solid pellets are supposed to behave. Pellets go through openings or bounce off barriers. Waves spread, overlap, and interfere. In 1927, Clinton Davison and Lester Germer observed electron diffraction when they scattered electrons from a nickel crystal. The electrons produced patterns that made sense if they were behaving as waves interacting with the regular atomic spacing of the crystal. Around the same time, George Thomson also showed electron diffraction by passing electrons through thin metal films. This was especially satisfying in a slightly mischievous way because George Thomson was the son of J.J. Thomson, who had discovered the electron as a particle. The father helped reveal the electron's particle nature. The son helped reveal its wave nature. Physics does enjoy a family plot twist now and then. These experiments gave strong support to de Broglie's idea. Electrons were not merely tiny charged balls. Under the right conditions, they behaved like waves. They could diffract. They could interfere. Their behaviour depended on wavelength, phase, and the structure they encountered. Matter had learned to ripple. This helped make sense of a deep problem inside the atom. In Bohr's model, electrons could occupy only certain allowed orbits, but the reason still felt partly imposed. Matter waves gave a more natural clue. A stable electron state could be imagined as a wave pattern that fits neatly around the atom, like a standing wave on a string or a musical note in a pipe. Only certain patterns fit cleanly. Others cancel themselves out or fail to form stable arrangements. The electrons' allowed states were not just arbitrary rules. They reflected wave behaviour at atomic scales. Later quantum mechanics would move beyond the picture of electrons as simple waves travelling in neat paths. It would describe electrons using wave functions, probability distributions, and orbitals rather than literal planetary orbits. But de Broglie's insight was still transformative. It showed that wave-particle duality was not only a strange feature of light, it belonged to matter as well. This changed what a particle meant. A particle was no longer simply a tiny object with a little path, like a grain of dust moving through sunlight. At the quantum level, matter could have a spread-out wave-like character, only becoming particle-like in particular interactions and measurements. The solid world had not disappeared. But beneath its firmness, reality had become less like a collection of miniature objects and more like a set of patterns, possibilities and rules that only reveal their shape when nature is carefully asked. The idea that matter could behave like a wave needed a new language. It was one thing to say that electrons had wavelengths, and another to describe exactly how those waves changed, moved, and shaped the behaviour of atoms. Physics needed something more precise than a picture, and less misleading than a tiny planet circling a tiny sun. In 1926, Erwin Schrodinger provided one of the great new languages of quantum mechanics. He developed wave mechanics, a way of describing quantum systems through something called a wavefunction. The wavefunction became one of the central ideas in modern physics. It allowed scientists to calculate the possible behaviour of electrons, atoms, and other quantum systems with remarkable accuracy. It was not just a decorative mathematical flourish, which is good, because physics already had quite enough symbols wandering around looking important. At first, it is tempting to imagine the wave function as a real physical wave, like a ripple spreading across a pond or a sound wave travelling through air. That image can help a little, but only at the beginning. A water wave is a disturbance in water. A sound wave is a pattern of pressure in air. The quantum wave function is stranger. It is a mathematical description of a quantum system, and it contains information about what may be found when that system is measured. For an electron in an atom, the wave function does not simply tell us that the electron is a small object following a hidden path. Instead, it describes the possible outcomes of measurement. It can be used to calculate where an electron is likely to be detected, what energy it may have, or how it may behave when it interacts with light or another particle. This was a major change from classical physics. In the older picture, probability usually meant ignorance. If the path of a thrown stone seemed uncertain, that was because the observer lacked enough information about its speed, angle, air resistance, and surrounding conditions. The stone itself still had a definite path. Quantum probability was different. Max Born, one of the key figures in the development of quantum mechanics, gave the wave function its famous probability interpretation. Born argued that the wave function should not be read as a direct physical smear of matter, but as a way of calculating probabilities for measurement outcomes. In this view, quantum mechanics does not reveal a hidden classical certainty underneath the uncertainty. It gives the most precise predictions nature allows for what may be observed. This does not make the theory weak. In fact, it made quantum mechanics extraordinarily powerful. The wave function allowed physicists to predict the spectra of atoms, the behaviour of electrons, and the structure of matter with a level of success that classical mechanics could not approach. It replaced the old dream of saying exactly what every particle was doing at every moment with a different kind of exactness. Exact rules for probabilities. That may sound like a step backward at first, because certainty feels stronger than probability. But in science, strength does not come from sounding comforting. It comes from matching reality. Quantum mechanics matched experiments. It told physicists not what they wished nature was doing behind the curtain, but what could actually be calculated, tested, and confirmed. Reality was not becoming vague. It was becoming precise in a less familiar way. The rule governing the wave function is called the Schrodinger equation. In ordinary terms, it describes how a quantum wave function changes over time. If the wave function is the mathematical description of the system, then the Schrodinger equation is the rule that lets that description evolve. It tells physicists how the possibilities shift, spread, interfere, and develop as time passes. A spoken version of the idea might be expressed as, the energy of the system is equal to the quantum rule for how the wave function changes with time. The actual mathematical form is one of the most important equations in physics, but the essential point is calmer than the notation suggests. Give the equation the right information about a system, and it tells you how the quantum state develops, not as a list of definite little paths, but as a structured pattern of possible outcomes. This helped explain atoms in a far deeper way than Bohr's earlier model. Bohr had suggested that electrons occupy certain allowed orbits, but Schrödinger's wave mechanics showed why stable quantum states could exist as wave patterns. Electrons in atoms are described by orbitals, not by neat circular tracks. An orbital is a region of probability shaped by the wave function. It tells us where an electron is more or less likely to be found if measured. Some orbitals are roughly spherical, while others have more complicated shapes, like lobes or rings. They are not little racetracks, they are probability structures. This was a profound shift in the meaning of physical description. Classical physics had aimed to describe what objects are doing. Quantum mechanics described what can be known, what can be measured, and how probabilities evolve before measurement. The world was still lawful, but its laws were no longer the laws of tiny billiard balls moving along invisible tracks. Schrodinger himself was not entirely comfortable with all the philosophical consequences of the theory he helped create. Like Einstein, he hoped for a clearer underlying picture than the one quantum mechanics seemed to offer. Yet his wave equation became one of the foundations of the new physics. It gave scientists a way to work with the quantum world even when that world refused to look like the ordinary one. The change was quiet but enormous. Reality was no longer described only through definite positions, definite paths, and definite outcomes waiting to be uncovered. It was described through wave functions, probabilities, and measurement results. The old clockwork dream did not vanish completely. It still works beautifully in the everyday world. But beneath that world, Schrödinger's wave introduced a new language of possibility, and possibility turned out to be written into nature with astonishing precision. Werner Heisenberg approached the quantum world from a slightly different direction. While Erwin Schrödinger gave physics a flowing language of waves, Heisenberg began with something more austere, more abstract, and in some ways more radical. In 1925, before Schrödinger's wave mechanics appeared, Heisenberg developed matrix mechanics, the first complete formulation of quantum mechanics. Matrix mechanics did not begin by asking what electrons look like inside atoms. It did not try to draw their paths or imagine them circling a nucleus in tiny loops. Heisenberg was suspicious of pictures that could not be directly tested. Instead, he focused on quantities physicists could actually observe, especially the frequencies and intensities of spectral lines. Atoms emitted and absorbed light in definite patterns. Those patterns were measurable. Whatever the atom was doing, the evidence came through those measured results. This was a major shift in scientific attitude. Classical physics had usually tried to describe an underlying motion and then calculate what would be observed from it. Heisenberg almost reversed the habit. He treated the observable results as primary and built the theory around them. Rather than asking where an electron really was in its unseen orbit, he asked what transitions between energy states could be measured. The hidden picture was no longer trusted simply because it felt familiar. The mathematics Heisenberg used involved arrays of numbers called matrices. These matrices represented physical quantities such as position, momentum, and energy. The strange feature was that, in quantum mechanics, the order of certain operations mattered. Handling position and then momentum did not always give the same result as handling momentum and then position. That may sound like a small mathematical inconvenience, but it pointed towards something deep. In the quantum world, some properties could not be treated as if they were all neatly defined in the same classical way. A few years later, this insight became one of the most famous principles in all of physics, the Heisenberg uncertainty principle. It is also one of the most often misunderstood. The uncertainty principle does not simply say that measuring tiny things is difficult. It is not caused by shaky hands, dusty lenses, impatient scientists, or laboratory equipment having a bad afternoon. Better instruments can reduce many practical errors, but the uncertainty principle describes a fundamental limit built into quantum systems themselves. The best-known version concerns position and momentum. Position means where a particle is. Momentum is connected to how much motion it has, depending on its mass and velocity. In spoken terms, the uncertainty principle says that the more precisely a particle's position is defined, the less precisely its momentum can be defined. And the more precisely its momentum is defined, the less precisely its position can be defined. This is not just a statement about what humans happen to know. It reflects the wave-like nature of matter. A wave with a very well-defined wavelength has a clear momentum, but it is spread out over space, so its position is not sharply fixed. A wave squeezed into a narrow region has a clearer position, but it must be made from a mixture of wavelengths, which means its momentum becomes less sharply defined. The uncertainty comes from the structure of the quantum description itself. This changed the meaning of knowledge in physics. In the old classical dream, a particle could have an exact position and an exact momentum at the same time, even if nobody knew both. Ignorance belonged to the observer, not to nature. Quantum mechanics made that assumption unsafe. Certain pairs of properties are not merely difficult to discover together. They are not simultaneously definite in the old classical sense. This does not mean the universe is chaotic or lawless. The uncertainty principle is not a loophole through which anything can happen. It is a precise rule with measurable consequences. It helps explain why electrons do not simply collapse into atomic nuclei. If an electron were confined too tightly near a nucleus, its momentum would become highly uncertain, increasing its kinetic energy. In this way, uncertainty is not just a philosophical inconvenience, it contributes to the stability of matter itself. Another quantum rule also helps explain that stability, the Pauli exclusion principle. Wolfgang Pauli introduced this principle in 1925. It states that identical fermions cannot occupy the same quantum state. Fermions include electrons, protons, and neutrons, though the electron is the most important example for ordinary chemistry. Because electrons cannot all pile into the same lower state, atoms develop structured shells and energy levels. This rule is one reason the periodic table has its shape. It helps explain why elements have different chemical properties, why atoms occupy space, and why matter does not simply collapse into a featureless dense blob. The Pauli exclusion principle is also essential in extreme astrophysical objects such as white dwarfs, where electron degeneracy pressure helps support the star against gravity. A rule discovered to explain atomic behavior turns out to matter in the quiet glow of dead stars. Physics has a habit of connecting the very small with the very large, as if the universe enjoys tidy bookkeeping. Together, Heisenberg's uncertainty principle and Pauli's exclusion principle made it clear that quantum mechanics was not merely adding new details to classical reality. It was changing the basic meaning of physical properties. Position, momentum, energy levels, and quantum states could no longer be treated as if they were all ordinary hidden facts waiting for a careful observer. Reality was still real. Measurement was still meaningful. Experiments still gave reliable results. But the old promise of complete knowledge had been limited from within. The universe was not a clockwork machine whose exact microscopic details could all be known at once, at least not in the way Laplace had imagined. At its deepest measured level, nature placed boundaries around certainty. That boundary was not a failure of science, it was one of science's discoveries. Quantum mechanics did not simply tell physicists that they knew less than they hoped. It showed them that reality itself was arranged differently from the classical dream. Some questions could be asked with extraordinary precision, but not all at once. The world had not become meaningless. It had become more subtle, and the limits of knowledge had become part of the laws of nature. Few experiments have done more to unsettle the ordinary picture of reality than the double-slit experiment. It is simple enough to describe with calm confidence, and strange enough to make that confidence quietly leave the room. At its heart, the experiment asks what happens when light, or matter, is given two possible paths and then allowed to reveal itself on a screen. The story begins long before quantum mechanics, with Thomas Young in the early 19th century. Young used the double-slit experiment to show that light behaves like a wave. When light passes through two narrow openings, the waves emerging from those openings spread out and overlap. Where the crests of the waves meet, they reinforce each other and make a brighter region. Where a crest meets a trough, they cancel and make a darker region. The result is an interference pattern, a series of bright and dark bands. This behavior is easy to picture with water. Imagine gentle ripples passing through two gaps in a barrier. On the other side, two spreading ripple patterns overlap. In some places, the water rises higher because the ripples combine. In other places, the surface becomes calmer because one ripple cancels another. Nothing about that seems especially mysterious. It is ordinary wave behavior, and for light it helped confirm that light could not be understood as only a stream of little particles. But quantum mechanics made the double-slit experiment much stranger. The same basic arrangement can be used with electrons, photons, and other quantum objects. If many electrons are fired toward two slits, they build up an interference pattern on the detection screen. That already suggests wave-like behavior, but the deeper strangeness appears when the particles are sent one at a time. If electrons were simply tiny solid pellets, each one should pass through one slit or the other and land on the screen. Over time, the pattern should look like two broad bands, matching the two openings. But when single electrons are sent through the double slit one after another, each electron is detected as a small individual hit on the screen. At first, the hits look random. Then, as more and more arrive, an interference pattern slowly emerges. That is the unsettling part. Each electron arrives as a single detected event like a particle. Yet the overall pattern looks as if each electron has somehow behaved like a wave passing through both slits and interfering with itself. The experiment seems to say that a quantum object cannot be understood as a tiny pellet, simply choosing a path in the ordinary way. Before measurement, its behavior is described by a wave function, a spread of possible outcomes that can interfere. This is not just a puzzle about human imagination, it is a real, measurable effect. Single photons can do this. Electrons can do this. Larger particles, including complex molecules under carefully controlled conditions, have also shown interference behavior. The larger and messier the object becomes, the harder it is to preserve the delicate quantum pattern, but the principle remains one of the clearest signs that the quantum world is not merely classical reality in miniature. Then comes the question of observation. What happens if a detector is placed near the slits to discover which path the particle takes? The answer is striking. When the experiment records path information, the interference pattern disappears. The particles behave as if they went through one slit or the other, and the screen shows a pattern more like ordinary particles passing through two openings. This does not mean a conscious person has to stare intensely at the experiment, perhaps with dramatic music playing softly in the background. In physics, observation means a physical interaction that creates information about the system. A detector, a measuring device, or the surrounding environment can all count if they make the path information available in principle. The key issue is not human attention. It is whether information exists that can distinguish the alternatives. This makes the double-slit experiment deeply connected to the meaning of reality. In classical physics, the question, which slit did the particle go through, seems simple. It must have gone through one, whether anyone checked or not. Measurement would merely reveal the pre-existing fact. Quantum mechanics does not allow that easy answer in the same way. If no path information exists, the system behaves according to a superposition of alternatives, and interference appears. If path information is created, the interference is lost. John Archibald Wheeler sharpened this puzzle with delayed choice experiments. Wheeler imagined versions of the experiment in which the decision about what kind of measurement to make is delayed until after the quantum object has already entered the apparatus. Later experiments inspired by this idea have shown results consistent with quantum theory. The point is not that consciousness travels backward in time or magically rewrites the past. That would be more bedtime chaos than bedtime science. The point is subtler. Quantum mechanics challenges the ordinary assumption that a particle's past path must always be a fixed classical story, independent of the measurement arrangement. The double-slit experiment shows that what happened can depend on what information can physically exist about the system. When no path information is available, the alternatives are not simply ordinary unknowns. They combine and interfere. When path information becomes available, even in principle, that interference vanishes. Reality at the quantum level is not just a list of hidden facts waiting to be uncovered. It is shaped by states, possibilities, interactions, and the conditions under which information becomes definite. The experiment remains powerful because it is visually simple and conceptually enormous. 2 slits, a screen, a source of particles, and from that small arrangement comes a challenge to the old idea that nature always has one clear observer-independent story written in classical terms. Quantum mechanics does not make reality unreal. It makes reality harder to simplify. Beneath ordinary experience, the world seems to preserve possibilities until the physical conditions of measurement force them into a form that can be recorded, counted, and known. Superposition is one of the ideas that makes quantum mechanics feel as if it is balancing quietly between sense and impossibility. In ordinary life, things appear to have settled properties. A lamp is on or off, a door is open or closed, a coin lands heads or tails. Even if a person has not looked yet, it feels natural to assume the answer is already there, waiting patiently for discovery. Quantum systems do not always fit that habit. Before measurement, a quantum system can be described as a combination of possible states. This is called quantum superposition. It does not mean, in a loose everyday way, that a particle is simply doing everything imaginable at once. It means something more precise and more subtle. The quantum state contains multiple possible outcomes, and those possibilities can combine, interfere, and evolve according to strict mathematical rules. One useful example is electron spin. Spin is a quantum property that behaves a little like angular momentum, though it should not be pictured too literally as a tiny electron rotating like a miniature planet. An electron can be prepared in a state where a measurement of spin could produce one result or another. Before the measurement, quantum mechanics describes the electron as being in a superposition of those possible spin outcomes. Once measured in a particular way, a definite result is found. Photon polarization offers another clear example. Light can be polarized, meaning its electromagnetic field has a certain orientation. A photon can be prepared in a superposition of different polarization states. When it passes through a polarizing filter, the outcome depends on the relationship between the photon state and the filter. The result is not just a hidden classical property being revealed in the old simple sense. The probabilities are shaped by the quantum state itself. Energy levels in atoms also involve this kind of thinking. An electron in an atom can be described by quantum states associated with particular energies. Under the right conditions, an atom can exist in a superposition of energy states before a measurement or interaction produces a definite outcome. This is not fantasy language. It is part of how real atomic clocks, spectroscopy, lasers, and quantum experiments are understood. The uneasiness comes from the fact that the mathematics works beautifully while the picture in the mind struggles to keep up. Paul Dirac helped give quantum mechanics some of its most powerful formal language. In the late 1920s, Dirac developed a concise and elegant way of describing quantum states, transformations, and measurement. His work helped unify different versions of quantum mechanics and later connected quantum theory with special relativity. Dirac's notation became a standard language of quantum physics because it treated quantum states not as vague images, but as precise mathematical objects. That mathematical structure matters. Superposition is not a poetic metaphor for uncertainty. It is a formal principle. Quantum states can be added together in ways that produce new valid states, and those combinations determine the probabilities of measurement outcomes. This is why quantum mechanics is not merely strange storytelling. It is strange storytelling with very strict bookkeeping, which is perhaps the most unsettling kind. The difficulty begins when this idea is pushed toward larger objects. In 1935, Erwin Schrodinger created his famous cat thought experiment to expose the awkwardness of quantum measurement. The setup imagines a cat in a sealed box with a quantum event, such as the decay of a radioactive atom, connected to a mechanism that could release poison. If the atom decays, the cat dies. If it does not decay, the cat lives. According to a simple application of quantum superposition, the atom might be described as being in a combination of decayed and not decayed states before measurement. If the cat's fate is tied to that event, then the whole arrangement seems to become a superposition of a live cat and dead cat. Schrödinger's point was not that cats are magical quantum creatures. He was not offering the world a charming pet-based proof that reality is whimsical. He was criticizing the awkwardness of applying quantum rules too directly to everyday objects. The cat was meant to make the measurement problem impossible to ignore. Where exactly does the superposition stop? Does it end when the atom interacts with the apparatus? When the apparatus affects the cat? When the box is opened? Or is the entire situation described by one large quantum state until a definite record exists? Modern physics answers parts of this through decoherence, where interactions with the surrounding environment rapidly destroy visible quantum interference for large objects. A cat is constantly interacting with air molecules, heat, light, and its own internal biological processes. It is not an isolated electron in a carefully controlled experiment, but decoherence does not remove the deeper philosophical puzzle completely. It helps explain why the everyday world appears definite, while leaving open questions about how exactly one outcome becomes the outcome that is experienced. Superposition changed the meaning of reality because it made possibility physically important. In classical thinking, possibilities often represent ignorance. A card is already face down on the table. The observer simply does not know which card it is. In quantum mechanics, the situation can be different. Before measurement, the system may not possess one definite classical property waiting underneath. Instead, it is described by a quantum state whose possible outcomes are real features of the theory. This does not mean anything can happen. Superposition is constrained by the wave function, by conservation laws, by the structure of the system, and by the kind of measurement being performed. Quantum mechanics is not a universe shrugging and saying, "Surprise me." It is a theory of possibility governed by precise rules. The uneasy middle of reality is this. Before measurement, quantum systems may not fit into the familiar categories of definite here or there, this or that, one path or the other. Yet after measurement, definite results appear. The world you experience is not a blur of every possibility. It is stable, specific, and shared. Quantum mechanics does not erase that world. It shows that beneath it, reality is not built from fixed properties alone, but from structured possibilities that become definite only through physical interaction. Superposition gives quantum mechanics its strange spread of possibilities, but measurement is where the strangeness becomes hardest to avoid. A wave function can describe several possible outcomes at once. It can evolve smoothly according to the Schrodinger equation. It can interfere, combine, and carry precise information about probabilities. Then a measurement happens, and one definite result appears. The detector clicks here, not there. The atom emits this photon, not that one. The electron is found with one spin result rather than the other. This is the measurement problem. Quantum mechanics predicts the probabilities of outcomes with extraordinary success, but it raises a deep question about how those possibilities become one observed fact. Before measurement, the wave function may contain a spread of possible results. After measurement, the world presents a single result that can be recorded, shared, and built into later events. The mathematics works beautifully. The conceptual picture is where the floorboards begin to creak. One way physicists describe this transition is wave function collapse. In the simplest telling, the wave function evolves as a spread of possibilities until measurement occurs. Then it appears to collapse into one outcome. If an electron has a probability of being detected in several possible places, the measurement finds it in one place. If a photon has possible polarization results, the measurement produces one result. Collapse is the name given to that apparent jump from many possible outcomes to one definite outcome. But the word collapse can be slightly misleading, because it can sound like a tiny physical object suddenly crumpling. The wavefunction is not a little balloon floating through space and then popping when a scientist looks at it. It is a mathematical description of a quantum state. Collapse means that after a measurement, the description is updated to match the single result that has actually been obtained. The difficulty is deciding whether this update is merely a change in knowledge, a real physical process, or a sign that the theory is incomplete. John von Neumann gave one of the most important formal treatments of measurement in quantum mechanics. He described the measurement process as a chain. A quantum system interacts with a measuring device. The device becomes correlated with the system. Then the result may be read by an observer. The problem is that if everything is treated quantum mechanically, the chain can keep extending. The system, the measuring device, and even the observer could be included in one larger quantum description. That raises the awkward question of where exactly the definite outcome appears. This is sometimes called the von Neumann chain. It is not a literal chain clanking across a laboratory bench, which is a shame, because at least that would be easier to find. It is a way of showing that measurement is not as simple as it first appears. If quantum mechanics applies to atoms, and atoms make up measuring devices, and atoms also make up human bodies, then why should the measuring device be treated as classical, while the tiny system is treated as quantum? Where does the boundary belong? The word observer often causes confusion here. In everyday language, an observer sounds like a conscious person watching carefully, perhaps with a clipboard and an expression of growing concern. But in physics, an observer does not necessarily mean a human mind. Measurement is about physical interaction and the creation of a stable record. A detector can observe, a photographic plate can observe, a particle interacting with its environment can, in a practical sense, create information that changes what interference patterns remain possible. This matters because quantum mechanics does not require consciousness to make reality happen. That idea appears often in popular accounts, but it is not the careful scientific claim. The central issue is not whether someone is looking with awareness. It is whether information about the system has become physically available, recorded, or entangled with the measuring apparatus or environment. Once the path of a particle is recorded, even in principle, the quantum behavior changes. The universe does not seem to be waiting for a human to notice, which is probably healthy for the universe's self-esteem. The Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg, approached these questions in a practical way. It emphasized what can be said about experimental arrangements and measurement outcomes, rather than trying to build a clear hidden picture of what exists between measurements. Bohr argued that the meaning of quantum properties depends on the complete experimental context. A system may reveal wave-like behavior in one arrangement and particle-like behavior in another. The two descriptions are complementary, not simply competing. This was not an easy view for everyone to accept. Einstein disliked the idea that physics should give up on a deeper description of reality. Schrodinger also found the implications uncomfortable. Yet the Copenhagen approach became influential because it matched how quantum mechanics worked in practice. Physicists could prepare systems, calculate probabilities, perform measurements, and compare predictions with results. The theory did not always satisfy the desire for a familiar picture, but it satisfied the stricter demand of experiment. The measurement problem sits at the heart of how quantum mechanics changed the meaning of reality. Classical physics treated measurement as a passive act. A planet had a position before anyone observed it. A stone followed a path whether or not anyone calculated it. Measurement simply revealed a fact that was already there. Quantum mechanics made that simple picture harder to defend at small scales. Some properties do not seem to have definite values independent of the way they are measured. This does not mean reality is imaginary or that measurement creates the whole universe out of nothing. It means the connection between physical state, possible outcome, and recorded fact is deeper than classical physics expected. Quantum mechanics can tell us with astonishing precision what probabilities should be. It can predict atomic spectra, semiconductor behavior, lasers, and countless experimental results. but the exact meaning of the transition from possibility to outcome remains one of its most persistent questions. At the boundary of measurement, reality becomes difficult to summarize in ordinary language. Before measurement, quantum theory speaks in wave functions and probabilities. After measurement, the world speaks in records, marks, clicks, numbers, and facts. Somewhere between those two descriptions lies the problem nobody quite escaped, and that is why quantum mechanics did not merely change physics. It changed what it means to ask what is real before reality has been measured. Entanglement is one of the places where quantum mechanics stops merely being strange and becomes almost impolite. It takes the old classical idea of separate objects, each carrying its own private properties, and quietly complicates it. In ordinary life, separation feels simple. One object is here, another object is over there. Whatever happens to one should not instantly depend on what happens to the other, unless a signal or force travels between them. Quantum entanglement challenges that comfortable picture. When two or more quantum systems become entangled, they cannot always be fully described as separate independent things. Their shared quantum state must be treated as a whole, even if the individual parts later move far apart. The particles may be distant, but the description of their possible measurement outcomes remains connected. A simple analogy is a pair of gloves. Imagine placing a left glove in one box and a right glove in another, then sending the boxes to opposite sides of the world. If someone opens one box and finds the left glove, they instantly know the other box contains the right glove. But nothing mysterious has happened. The gloves had their properties all along. The information was merely hidden until someone looked. Entanglement is deeper than that. It is not just a case of particles carrying prearranged answers like matching gloves or cards placed secretly into envelopes. Entangled particles can produce correlations that are stronger than any ordinary hidden arrangement should allow. Their measurement results are linked in a way that cannot be fully explained by saying each particle simply carried a definite instruction from the start. This became sharply important in 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen published a famous argument now known as the Einstein-Podolsky-Rosen argument. They were not trying to celebrate quantum mechanics. Quite the opposite. They wanted to show that the theory might be incomplete. Their reasoning focused on systems that had interacted and then separated, while remaining described by a shared quantum state. Einstein, Podolsky, and Rosen argued that if quantum mechanics were complete, then measuring one part of the system seemed to affect what could be said about the distant part. That appeared to conflict with a principle Einstein cared about deeply: locality. Locality means that physical influences should not travel faster than light. Since special relativity treats the speed of light as the cosmic speed limit for signals and causal influence, any hint of instantaneous distant connection looked deeply suspicious. Einstein disliked this implication. He famously objected to what he called spooky action at a distance. The phrase captures the discomfort beautifully. It was not that Einstein rejected experimental evidence or disliked strangeness for dramatic reasons. He had helped create quantum theory himself. His concern was that quantum mechanics seemed to abandon a deeper, more complete description of physical reality. The key idea at stake was local realism. Realism, in this context, means that objects possess definite properties independent of measurement. Locality means that distant events cannot instantly influence each other. Together, local realism gives a very natural picture of the world. Things have their own properties, and influences spread through space in an orderly way, no faster than light. It feels sensible, it feels stable, it feels like the sort of reality that would remember to lock the door before going to bed. Entanglement unsettles that picture. Suppose two particles are created together in an entangled state, and then sent in opposite directions. When one is measured, its result is correlated with the result of the other. Quantum mechanics predicts these correlations very accurately. The unsettling part is that the correlations cannot be explained in the same way as the gloves. It is not enough to say the particles had simple, definite values waiting inside them all along, at least not if locality is preserved in the classical sense. Still, entanglement does not allow faster-than-light messaging. This point matters because the phrase spooky action can easily be misunderstood. Measuring one entangled particle does not let someone choose a message and send it instantly to the other side of the galaxy. The individual result is random. Only when the two sets of results are later compared through ordinary communication do the special correlations become visible. So entanglement challenges classical locality, but it does not turn the universe into a cosmic instant messaging service. The galaxy remains spared from that notification problem. The power of entanglement is that it shows quantum systems are not always built from independent parts, with independent properties. Sometimes the whole quantum state carries information that cannot be reduced to each piece separately. The relationship is not an added detail. It is part of what the system is. This is why entanglement matters so deeply to the meaning of reality. Classical thinking imagined that the world could be divided into separate objects, each with definite properties, whether or not anyone looked. Quantum mechanics showed that this division is not always possible. Some properties only become definite within the context of measurement, and some correlations belong to the shared state of systems rather than to either part alone. Einstein hoped this meant quantum mechanics was unfinished. Perhaps hidden variables, deeper properties not yet included in the theory, would restore a more classical reality underneath. That possibility would later be tested with Bell's theorem and real experiments. But even before those tests, entanglement had already revealed the shape of the problem. Quantum mechanics was not merely uncertain, it was non-classical in how separate things could be related. Reality had refused to stay neatly local in the old intuitive way. Not by allowing magical signals, and not by making distance meaningless, but by showing that the quantum description of nature can connect systems more deeply than classical objects allow. The universe was still lawful, it was still measurable, but its parts were not always as separate as they seemed. Entanglement raised a disturbing question, but for a while it remained possible to wonder whether quantum mechanics was simply hiding something. Perhaps particles really did carry definite properties all along. Perhaps the theory only looked strange because it was incomplete. Maybe, beneath the probabilities and measurement puzzles, there was a deeper classical order waiting to be discovered. This was the hope behind local hidden variable theories. The idea was that quantum particles might possess hidden properties not included in the standard wave function. These hidden variables would determine the results of measurements while preserving locality, the principle that no physical influence travels faster than light. If that were true, then entanglement might be less mysterious than it appeared. The particles could simply carry prearranged instructions from the moment they separated, like sealed envelopes containing matching answers. For many years, this seemed like a philosophical debate more than an experimental one. Quantum mechanics predicted results. Einstein, Podolsky, and Rosen argued that those results suggested the theory was incomplete. Niels Bohr defended the quantum view. The disagreement was deep, but it was not obvious how to settle it in a laboratory. Reality, as usual, had chosen to be both measurable and annoyingly subtle. Then, in 1964, John Bell changed the situation. Bell was a physicist from Northern Ireland who worked at the European Organisation for Nuclear Research, better known as CERN. He found a way to turn the argument about hidden variables into something testable. His result is now known as Bell's theorem, and it is one of the most important discoveries in the foundations of quantum mechanics. Bell showed that if local hidden variable theories were correct, then the correlations between measurements on separated particles would have to obey certain limits. These limits are called Bell inequalities. In plain terms, Bell inequalities describe how strongly two separated systems can be connected if their properties were fixed beforehand, and if no faster-than-light influence is allowed between them. They are like a boundary drawn around the older common-sense picture of reality. Quantum mechanics predicted that entangled particles could cross that boundary, not by sending messages faster than light, and not by allowing anyone to control distant outcomes, but by producing correlations stronger than local hidden variable theories could permit. That was the brilliance of Bell's work. He did not simply say that quantum mechanics was strange. He showed how to test whether the strangeness could be explained by a deeper local classical reality. The first major experimental tests came in the following decades. John Clauser carried out important early work in the 1970s, testing Bell inequalities with entangled photons. Then, in the early 1980s, Alain Aspect and his colleagues in France performed a series of influential experiments using pairs of entangled photons. These experiments strongly supported the predictions of quantum mechanics and found violations of Bell inequalities. That phrase, violations of Bell inequalities, sounds calm and technical, almost as if reality had merely filled in the wrong form at a physics office. But the meaning is profound. The results suggested that nature cannot be explained by any theory that keeps both locality and the idea of pre-existing measurement outcomes in the simple classical form Bell tested. At least one part of the older worldview had to be given up. Later experiments made the case stronger by closing more and more possible loopholes. In experimental physics, a loophole is not an excuse to ignore a result. It is a possible weakness in the setup that must be tested more carefully. Some early Bell tests had detection loopholes, where not every particle was successfully measured. Others had locality loopholes, where the measurement settings might not have been separated clearly enough to rule out ordinary communication. Over time, researchers built more refined experiments to address these issues. Groups associated with Delft University of Technology performed important loophole-free Bell tests using entangled electron spins in diamond. Researchers connected with the National Institute of Standards and Technology carried out major photon-based Bell tests with high-efficiency detectors. Work associated with the University of Vienna and Anton Zeilinger's group also played a central role in advancing entanglement experiments, quantum teleportation, and tests of quantum foundations. The technical details are intricate, but the broad message is clear. Careful experiments kept pointing back to the same conclusion. Quantum mechanics was not merely an awkward theory waiting for classical common sense to rescue it. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger for experiments with entangled photons, tests of Bell inequalities, and pioneering work in quantum information science. Their recognition marked something remarkable. A debate that had once seemed almost philosophical had become a pillar of modern experimental physics. The question of what reality allows had moved from thought experiments into laboratories, detectors, photon sources, and statistical tests. Bell's theorem did not say that everything is mysterious in some vague decorative way. It said something sharper. If quantum predictions are correct, and experiments overwhelmingly support them, then reality does not fit the old combination of local causes and definite pre-existing properties. The universe may still obey relativistic limits on signaling. It may still prevent faster-than-light communication, but it does not behave as if separated particles always carry simple hidden answers that merely wait to be revealed. This is why Bell's theorem cornered reality. It gave nature a choice, and nature did not choose the comfortable classical option. The world at small scales is not just unknown before measurement in the way a hidden playing card is unknown. It is governed by correlations that cannot be reduced to ordinary local instructions written in advance. Quantum mechanics had sounded strange from the beginning. Planck's quanta, Einstein's photons, Bohr's atoms, Schrödinger's wavefunction, Heisenberg's uncertainty and entanglement all strained ordinary intuition. But Bell's theorem and the experiments that followed did something even more important. They showed that the strangeness was not just a failure of imagination, it was written into the measurable behaviour of the world. Reality had been tested, patiently and repeatedly, and it declined to become classical again. The strange part of quantum mechanics is not only that small things behave strangely, It is that large things usually do not. A single electron can show interference. A photon can be placed in a superposition of possible paths. A carefully isolated atom can reveal delicate quantum behavior, yet a chair does not seem to sit in two places at once. A cup of tea does not spread across the room as a wave of possible refreshments. The everyday world looks reassuringly ordinary. Quantum decoherence helps explain why. Decoherence is the process by which a quantum system loses its visible interference behavior through interaction with its environment. In a clean, isolated experiment, a quantum system can preserve delicate relationships between different parts of its wave function. These relationships are often called phase relationships. They are what allow possibilities to interfere, combining in some outcomes and cancelling in others. But once the system interacts with the outside world, that delicate structure becomes entangled with the environment. The environment is not just the air in the room, though air is certainly involved and rarely misses a chance to interfere. It includes photons of light, heat radiation, surrounding surfaces, nearby particles, vibrations, and anything else capable of carrying away information about the system. Every little interaction spreads quantum information outward. The system is no longer cleanly separate. Its possible states become linked with countless environmental details. H. Dieter Z was one of the first physicists to develop the idea of decoherence seriously, beginning in the 1970s. Wojciech Zurek later became one of the key figures in explaining how decoherence helps produce the appearance of a classical world. Their work showed that the boundary between quantum strangeness and everyday definiteness does not require a mysterious curtain suddenly dropping between the small and the large. Instead, ordinary objects are constantly interacting with their surroundings in ways that make quantum interference effectively impossible to observe. This is why large objects do not appear in obvious superpositions. A dust grain floating in sunlight is bombarded by photons. It collides with air molecules. It radiates and absorbs heat. It interacts with the electromagnetic fields and nearby surfaces. Each interaction carries away a little information about where the dust grain is and what state it is in. The result is that any fragile superposition involving different positions becomes decohered extremely quickly. The same is true, even more dramatically, for everyday objects. A cat, a table, or a person is not an isolated quantum system. Each is made of enormous numbers of particles, constantly interacting internally and externally. Heat moves, molecules vibrate, light scatters, air presses, surfaces touch, information leaks into the environment at an extraordinary rate. The visible quantum interference that can be preserved in a carefully shielded laboratory system is washed out almost instantly in ordinary conditions. A useful comparison is a quiet conversation in a crowded room. If two people whisper in perfect calm, the words may be clear. But if hundreds of voices, footsteps, clinking cups, and distant music fill the room, the delicate pattern of the whisper becomes practically impossible to recover. The information has not simply vanished in a magical sense. It has become dispersed into the wider noise. Decoherence works in a similar spirit. The quantum phase relationships that would allow interference become spread into the environment, inaccessible to anything like ordinary measurement. Another comparison is footprints in wet sand. A clear footprint can hold a shape for a moment, but rain, waves, wind, and passing feet quickly blur it. The mark is not erased by one dramatic event. It becomes part of a larger pattern of disturbances. With quantum decoherence, the original delicate pattern of possibilities becomes entangled with so many surrounding degrees of freedom that the interference between alternatives can no longer be seen. This is important because it explains why the world looks classical without denying quantum mechanics. Classical behavior emerges because large, warm, messy systems are almost never isolated from their environments. Their quantum possibilities do not remain neatly available for interference. Instead, the environment effectively selects stable patterns that behave like familiar, definite states. Zurek called part of this idea environment-induced superselection, often shortened to Einstein, though the full phrase is much kinder to a sleepy voiceover than the abbreviation. Decoherence also helps explain why measurement devices produce stable records. A detector does not remain in a delicate superposition that can easily interfere with itself. Its state becomes correlated with the environment. The result spreads into wires, screens, memory, heat, scattered photons, and eventually notebooks, computers, and possibly someone muttering, "That is odd," in a laboratory. A measurement outcome becomes robust because it is copied into the surrounding world, but decoherence does not solve everything. It helps explain why quantum interference disappears from practical view and why classical behavior emerges from quantum rules. It does not, by itself, fully answer every version of the measurement problem. Different interpretations of quantum mechanics still disagree about what decoherence means at the deepest level. Does it explain why one outcome is experienced? Does it only explain why alternatives stop interfering? Does it support many worlds, collapse theories, or a more practical Copenhagen-style view? Those questions remain debated. What decoherence does show is that everyday reality is not separate from quantum mechanics. It is not a different realm where quantum rules give up and wander off for a nap. The ordinary world emerges because quantum systems interact constantly with their environments. The strangeness becomes hidden not because it was false, but because it becomes spread too widely to reveal itself as interference. So quantum mechanics does not deny the familiar world. It explains why it appears. Chairs, tables, stones, and cups remain dependable because their quantum possibilities are entangled with a vast surrounding environment. The surface of reality looks solid and classical, but beneath it lies a deeper set of rules. The world seems ordinary, not because quantum mechanics stops working, but because it works everywhere at once. Quantum mechanics is one of the most successful theories science has ever produced. It predicts the behavior of atoms, light, matter, magnetism, chemistry, electronics, lasers, and many precision experiments with astonishing accuracy. In some areas, its predictions match observation to a level so fine that ordinary language starts to look a little underdressed for the occasion. As a tool for calculation, quantum mechanics works beautifully. But understanding what the mathematics means is another matter. This is where interpretations enter the story. The equations of quantum mechanics tell physicists how to calculate probabilities and predict measurement outcomes. They tell how wave functions evolve, how quantum states combine, and what results should appear in experiments. Yet they do not force everyone to agree on one simple picture of what is happening behind those predictions. Different interpretations accept the same core experimental success, but tell different stories about what the theory says reality is. The Copenhagen interpretation is the most historically famous. Associated especially with Niels Bohr and Werner Heisenberg, it grew from the early development of quantum mechanics in the 1920s. It treats measurement as central. Rather than insisting on a hidden classical picture of what particles are doing between observations, it focuses on what can be said about experimental arrangements and their outcomes. Bohr's idea of complementarity was especially important. A quantum system can show wave-like behavior in one experimental setup and particle-like behavior in another. These are not simply contradictions, but complementary ways the same underlying system can appear under different conditions. The strength of the Copenhagen interpretation is its practicality. It tells physicists not to demand a tiny clockwork story where none is available. Prepare the system, describe the measurement, calculate the probabilities, compare them with the results. It does not always soothe the philosophical itch, but it has guided generations of working physicists. Sometimes, in science, a view becomes powerful not because it makes everyone comfortable, but because it helps them stop arguing long enough to calculate something. Hugh Everett III offered a very different picture in 1957. His many worlds interpretation treats the wave function as never collapsing. Instead, the wave function continues to evolve smoothly, and measurement becomes a branching process. When a quantum event has several possible outcomes, All outcomes occur in different non-communicating branches of reality. In this view, there is no special collapse at measurement. There is only the universal wave function, evolving according to quantum rules. Many worlds is startling because it takes the mathematics very seriously, perhaps more seriously than human intuition would prefer at bedtime. It removes the need for a collapse mechanism, but it does so by accepting an enormous branching structure of outcomes. Supporters see this as elegant and consistent. Critics question whether it adds too much invisible reality, or whether its branches can be understood in a fully satisfying way. Either way, it shows how far interpretation can move while still preserving the same successful predictions. David Bohm developed another alternative known as pilot wave theory or Bohmian mechanics. In this interpretation, particles do have definite positions, but they are guided by a wave. The wave evolves according to quantum rules and directs the motion of the particles. This restores a clearer kind of particle reality, which may sound comforting at first. But the cost is non-locality. The guiding wave can connect distant parts of a system in ways that do not fit the older classical idea of strictly local influence. Pilot wave theory is valuable because it shows that quantum mechanics does not logically force every possible classical idea to vanish. Definite particle positions can be restored, but not for free. The price is a universe where the guiding structure is deeply non-local. Reality can regain one familiar feature only by surrendering another. Objective collapse theories take yet another route. Instead of treating collapse as a mere update in knowledge, they propose that collapse is a real physical process. The Girardi-Rimini-Weber model is one of the best-known examples. It suggests that wave functions spontaneously collapse under certain conditions, especially as systems become larger or more complex. This could explain why microscopic systems show quantum superposition, while everyday objects appear definite. The appeal of objective collapse theories is that they try to modify the physics in a way that may, in principle, produce testable differences. They do not merely say, here is a different story for the same equations. They ask whether the equations themselves may need a small but meaningful addition. That makes them scientifically interesting, even though no collapse model has yet replaced standard quantum mechanics as the accepted framework. Not all interpretations have the same scientific status. Some mostly offer different ways of thinking about the same predictions. Others suggest possible new experiments. The value of an interpretation depends partly on whether it clarifies the theory, removes confusion, generates testable predictions, or helps guide future work. A beautiful picture is not enough by itself. In physics, beauty still has to report to experiment. This is one of the strangest legacies of quantum mechanics. It separated predictive success from philosophical comfort. Classical physics gave people pictures they could imagine: planets orbiting, stones falling, waves spreading, gears turning. Quantum mechanics gave science something more powerful but less cozy. A theory that predicts reality with extraordinary precision while resisting one simple image of what reality is underneath. The meaning of reality changed because the same mathematics could support multiple serious interpretations. The world did not become unreal. The experiments did not become optional. But the old demand for one obvious picture no longer worked. Quantum mechanics left science with a theory that behaves like a perfectly tuned instrument, while the question of what music it is really playing remains even now quietly unresolved. After all the debates about measurement, interpretation, and what reality may be doing before anyone checks, it is useful to come back to something wonderfully concrete. Quantum mechanics is not only a theory for laboratories, thought experiments, and arguments that make physicists stare quietly into cups of coffee. It is also the reason matter has structure. It is why atoms bond, why chemistry works, and why the familiar world does not collapse into a dull, featureless fog. Every ordinary object is built from atoms, and atoms are organized by quantum rules. Electrons do not arrange themselves around nuclei like tiny planets, with tiny diaries and reliable orbital schedules. They occupy atomic orbitals, which are patterns described by wavefunctions. These orbitals tell us where electrons are likely to be found and what energies they can have. Their shapes and energies determine how atoms behave when they meet other atoms. One of the most important rules behind this structure is the Pauli exclusion principle, introduced by Wolfgang Pauli. It states that identical fermions cannot occupy the same quantum state. Electrons are fermions, so they cannot all crowd into the lowest available state around an atom. Instead, they fill available states in an orderly way, creating shells and subshells. This is one of the deep reasons the periodic table has its structure. The periodic table is not just a convenient chart hanging on a classroom wall, silently judging everyone who has forgotten where molybdenum goes. It is a map of quantum organization. Hydrogen behaves differently from helium because its electron structure is different. Carbon forms rich chains and complex molecules because of the way its electrons are arranged. Sodium reacts strongly with chlorine because their outer electrons make certain exchanges energetically favorable. The diversity of elements depends on quantum energy levels, electron configurations, and the exclusion principle. Quantum mechanics also transformed chemistry. Before the quantum era, chemists had discovered many patterns of reaction, bonding, and composition. They knew that substances combined in reliable ways, and they developed powerful rules for predicting chemical behavior. But quantum mechanics explained why those rules worked at a deeper level. It showed how electrons create bonds, how molecules take particular shapes, and why different arrangements of atoms have different energies. Linus Pauling was one of the major figures in bringing quantum mechanics into chemistry. His work on chemical bonding helped explain how atoms share or transfer electrons, and how the shapes of molecules arise from the behavior of orbitals. He showed that chemistry was not merely a catalogue of reactions, but a physical theory of structure. Molecules could be understood as quantum systems, with electrons distributed in ways that hold nuclei together. A covalent bond forms when atoms share electrons. In a water molecule, for example, oxygen and hydrogen are held together because electrons are shared in a stable arrangement. The shape of water is not accidental. Its bent structure comes from the quantum behavior of electrons around the oxygen atom, and that shape helps give water its remarkable properties. Without that molecular geometry, oceans, clouds, ice, cells, and cups of tea would be very different, and not in a charming way. An ionic bond works differently. In ordinary table salt, sodium tends to lose an electron, and chlorine tends to gain one, forming oppositely charged ions. These ions attract each other and arrange into a crystal lattice. The result is sodium chloride, a solid structure built from electrical attraction and quantum-governed electron configurations. Even something as familiar as salt on chips depends on the hidden rules of atomic structure. Molecular orbitals take this further. In molecules, electrons are not always best thought of as belonging to one atom or another. They can be described by orbitals spread across several atoms. This helps explain materials such as diamond and graphite. Both are made from carbon, yet diamond is hard and transparent, while graphite is soft and dark. The difference lies in how carbon atoms bond and how electrons are arranged across their structures. Same element, very different behavior. Carbon, it seems, enjoys a costume change. Proteins also depend on quantum chemistry, though it is important to be careful here. Life is not a vague cloud of mystical quantum magic. Biology is mostly explained through chemistry, molecular structure, thermodynamics, and evolution. But chemistry itself is quantum underneath. The shapes of proteins, the behavior of enzymes, the structure of DNA, and the interactions between molecules all depend on electrons, bonds, charges, and energy levels governed by quantum mechanics. Quantum tunneling is one especially interesting phenomenon. Tunneling occurs when a particle has a chance of passing through an energy barrier that classical physics would say it cannot cross. This does not mean particles casually walk through walls in everyday life, which is a relief for walls. At small scales, tunneling can matter enormously. It plays a role in nuclear fusion inside stars, where particles can overcome barriers more easily than classical physics alone would allow. It is also central to some semiconductor devices and scanning tunneling microscopes. In biology, tunneling may contribute to certain enzyme reactions, where electrons or protons move in ways that affect reaction rates. But the careful phrasing matters. Quantum effects can be relevant in biology without making all of life mysterious or magical. The strongest scientific claim is that some biological processes use ordinary chemistry, and ordinary chemistry rests on quantum rules. This brings quantum mechanics back from the edge of philosophy into the substance of the world. The theory did not only change arguments about measurement and reality, it explained why atoms are stable, why elements differ, why molecules form, why materials have properties, and why living systems can be built from carbon, water, proteins, and molecular machines. The familiar world exists because quantum mechanics gives matter structure. Reality changed not by becoming less real, but by becoming more deeply explained. Beneath every solid surface, every chemical reaction, and every living cell, there is a quiet quantum order holding the ordinary world together. Quantum mechanics can sound like a theory that belongs only in strange experiments, philosophical debates, and sealed boxes containing deeply inconvenienced imaginary cats. But its influence is much more practical than that. The same rules that made physicists rethink matter, light, and measurement also became the foundation beneath much of modern technology. The quantum world did not remain hidden inside laboratories. It quietly moved into pockets, hospitals, satellites, computers, cameras, and clocks. One of the clearest examples is the semiconductor. A semiconductor is a material whose ability to conduct electricity sits between that of a conductor and an insulator. Silicon is the most famous example. Its usefulness depends on the quantum behavior of electrons in solids, especially the way electrons occupy allowed energy bands. In a solid material, atoms are packed together so closely that their individual energy levels spread into bands. Some bands are filled, some are empty, and the gap between them determines how easily electrons can move. This is not just a technical detail. The band structure of materials explains why copper conducts electricity easily, why glass does not, and why silicon can be carefully controlled. By adding tiny amounts of other elements to silicon, a process called doping, engineers can change how many mobile electrons or electron vacancies are available. Those vacancies are often called holes, and they behave like positive charge carriers. This delicate control of electron behavior is only possible because quantum mechanics explains how electrons occupy energy states inside matter. From this came the transistor, one of the most important inventions in human history. At Bell Laboratories in 1947, John Bardeen, Walter Brattain, and William Shockley developed the first working transistor. A transistor can act as a switch or amplifier, controlling the flow of electric current. Modern computer chips contain enormous numbers of transistors arranged into circuits that process information. Phones, laptops, digital cameras, routers, cars, medical devices, and spacecraft all depend on them. The transistor is sometimes described as a tiny switch, which is useful but incomplete. It is a switch made possible by quantum physics, the behavior of electrons in semiconductor materials, the existence of energy bands, the movement of charge carriers, and in some very small devices even quantum tunneling, all matter. Modern technology is not built by ignoring the strangeness of quantum mechanics. It is built by making that strangeness reliable, repeatable, and politely useful. Lasers are another beautiful example. The word laser comes from light amplification, by stimulated emission of radiation. The central idea goes back to Albert Einstein, who described stimulated emission in theoretical work in the early 20th century. In stimulated emission, an incoming photon can cause an excited atom or molecule to emit a second photon with the same energy, direction, and phase. When this process is carefully controlled, it produces a beam of light that is highly ordered, narrow, and coherent. Charles Townes and Arthur Schawlow helped develop the theory behind masers and lasers, and Theodore Maiman built the first working laser in 1960 using a ruby crystal. Today, lasers are everywhere. They read data, scan barcodes, cut materials, carry information through optical fibers, guide medical procedures, and help measure distances with remarkable precision. A laser beam may look smooth and simple, but its existence depends on quantum energy levels and controlled photon emission. It is quantum mechanics turned into a very neat line of light. Medicine also depends on quantum ideas. Magnetic resonance imaging, usually called MRI, uses the quantum property of spin. Certain atomic nuclei, especially hydrogen nuclei in water and fat, behave like tiny magnetic systems when placed in a strong magnetic field. Radio waves can disturb their alignment, and as they relax back, they emit signals that can be used to build detailed images of the inside of the body. The physics grew from nuclear magnetic resonance, with important contributions from Isidore Rabi, Felix Bloch, and other researchers. An MRI scanner does not feel like a philosophical argument about reality. It feels like a large machine making loud knocking noises while someone tries very hard not to move. But beneath the noise is quantum physics being used with extraordinary care. The spin states of atomic nuclei, their interaction with magnetic fields, and the signals they produce all come from the quantum structure of matter. In hospitals, quantum mechanics becomes a way of seeing soft tissue, organs, tumours, injuries, and blood flow without cutting the body open. Quantum mechanics also shapes precision measurement. Atomic clocks use the stable frequency of transitions between energy levels in atoms, often cesium or other carefully controlled systems. Because these transitions are governed by quantum rules, they provide extraordinarily reliable time standards. Institutions such as the National Institute of Standards and Technology in the United States and the National Physical Laboratory in the United Kingdom work on these kinds of precision measurements and standards. Atomic clocks are essential for satellite navigation, telecommunications, scientific measurements, and global timing systems. A navigation system needs precise timing, because even tiny errors in time can become large errors in position. The calm voice giving directions in a car depends, somewhere far above, on clocks using quantum transitions with almost absurd precision. Reality may be strange, but it is punctual. This is why quantum mechanics changed more than the meaning of reality in a philosophical sense. Its rules are not vague curiosities. They are dependable enough to build the modern world around. The same theory that says particles can behave like waves, electrons occupy quantum states, and energy comes in discrete levels also allows engineers and doctors to build computers, lasers, scanners, solar cells, satellites, and clocks. Quantum mechanics made reality stranger, but not weaker. If anything, it showed that the world's deep strangeness could be trusted. The hidden rules beneath matter and light are so consistent that entire technologies can rest on them. The universe may not behave like the old clockwork machine, but it is still lawful enough to guide a laser, switch a transistor, image a brain, and keep time across the planet. By the time quantum mechanics became the basis of technology, it had also become something else, a theory about information. Not information in the casual sense of notes, messages, or someone saying they definitely read the instructions when they absolutely did not. In quantum physics, information is tied to physical systems themselves. It is connected to states, measurements, correlations, probabilities, and what can be known about the world. Classical information is usually described in bits. A bit can be one of two values, like yes or no, on or off, true or false. Computers use physical systems to represent those values, but the logic is basically definite. A classical bit is in one state or the other. It may be stored in a transistor, a magnetic region, or an electrical signal, but at the level of information it behaves like a clear choice between two possibilities. Quantum information begins with the qubit. A qubit is a quantum system that can be described as a superposition of two basic states. These states might be the spin states of an electron, the polarization states of a photon, energy levels in an atom, or carefully controlled states in a superconducting circuit. Unlike a classical bit, a qubit is not simply one or the other before measurement. Its quantum state can contain a structured combination of both possibilities, with probabilities that depend on how the qubit is prepared and measured. This does not mean a qubit is a magical coin that is both heads and tails in the ordinary everyday sense. It means the qubit is described by a quantum state, and that state can interfere with itself, become entangled with other qubits, and produce measurement outcomes according to quantum rules. The power of quantum information comes from using superposition, entanglement, and interference in a controlled way. Richard Feynman helped inspire the idea of quantum computing by pointing out that quantum systems are difficult for classical computers to simulate efficiently. Since nature behaves quantum mechanically, perhaps a computer built from quantum principles could simulate quantum systems more naturally. David Deutsch developed the idea further by describing a universal quantum computer, a machine that could, in principle, perform any quantum computation. Quantum computers are often described as faster computers, but that is too simple. They are not just ordinary computers with a more energetic personality and a smaller patience budget. They process information differently. For some tasks, quantum algorithms can offer major advantages. Peter Shaw developed an algorithm showing that a sufficiently powerful quantum computer could factor large numbers far more efficiently than known classical methods, which has consequences for cryptography. Lovegrover developed a quantum search algorithm that can speed up certain kinds of unstructured search problems. But quantum computers are not automatically better at everything. They are delicate machines, vulnerable to noise and decoherence. Their qubits must be controlled with extreme care, and useful large-scale quantum computing remains a major engineering challenge. Organizations such as IBM Quantum, Google Quantum AI, and the University of Science and Technology of China have built increasingly advanced quantum processors, but the field is still developing. The promise is real, but so are the difficulties. Quantum mechanics, as usual, offers a door and then places several complicated locks on it. Quantum information also reshaped ideas about security. In 1984, Charles Bennett and Gilles Brasseur introduced a quantum key distribution protocol known as BB84. The central idea is that quantum measurement can reveal eavesdropping. If someone tries to intercept and measure certain quantum states used to create a secret key, the act of measurement can disturb those states in a detectable way. This does not make every communication magically unbreakable, but it shows how quantum physics can be used to build new forms of secure information exchange. Another striking idea is quantum teleportation. The name is dramatic enough to make science fiction lean forward, hopefully, but the real process is more careful. Quantum teleportation transfers an unknown quantum state from one system to another using entanglement and ordinary classical communication. No object is transported. No person disappears in one place and reappears somewhere else, which is probably a relief for anyone who distrusts complicated machinery, and no faster than light signal is sent. The classical communication step is essential, so relativity remains safe. Quantum teleportation shows how deeply information and physical reality are connected in quantum mechanics. The state of a system can be transferred without copying it in the ordinary sense, because unknown quantum states cannot be perfectly cloned. This no-cloning rule is another important feature of quantum information. It tells us that quantum information is not like a document that can be copied endlessly without consequence. It is tied to the physical state of the system itself. Research institutions across the world explore these ideas in different ways. The European Organisation for Nuclear Research, known as CERN, is best known for particle physics, but the wider world of quantum research reaches from particle laboratories to computing companies, national standards institutes, universities, and communication experiments. Quantum information is now a field where foundations, technology, and philosophy overlap. This brings the meaning of reality into a modern form. Information is not merely something written down after the world has already done its work. In quantum mechanics, information is part of how systems are described, how measurements are understood, and how physical limits are defined. What can be known, what can be copied, what can be measured, and what can be securely shared are all questions governed by the laws of physics. The theory that changed reality did not stop with particles and waves. It changed the meaning of information itself. At the quantum level, information is physical, fragile, structured, and deeply tied to measurement. Reality is not just made of things. It is also made of the rules that decide what can be known about things, and how that knowledge can exist in the world. Quantum mechanics changed the meaning of reality because it showed that the world beneath ordinary experience is not built like the clockwork universe imagined by classical physics. In the older picture, reality seemed to be made of objects with definite properties, moving along definite paths, shaped by forces in ways that could be predicted perfectly if enough information were known. A particle had a position, a planet had an orbit, a cause produced an effect. The world was difficult to calculate, certainly, but in principle it seemed fully knowable. Quantum mechanics did not simply add a few strange behaviours to that picture. It changed the foundation. At small scales, nature is described through quantum states, wave functions, probabilities, uncertainty relations, superposition, entanglement, and measurement rules. That does not mean reality became unreal. It means reality was found to be more subtle than the older picture allowed. This distinction matters, because quantum mechanics is often surrounded by dramatic misunderstandings. It does not prove that reality is imaginary. It does not prove that consciousness creates the universe by looking at it. It does not mean thoughts can bend matter through belief, or that anything can happen if someone simply feels mysterious enough about it. The actual theory is far stricter, more precise, and in some ways, more astonishing than those claims. Quantum mechanics is not a permission slip for fantasy. It is a mathematical and experimental framework that has survived some of the most careful tests in science. What it does show is that energy can come in quantized amounts. Light can behave as both a wave and as individual photons. Matter can have wave-like properties. Electrons in atoms are described by orbitals and probabilities, not by tiny planetary paths. Some pairs of properties, such as position and momentum, cannot both be perfectly definite at the same time. A quantum system can be described as a superposition of possible outcomes before measurement. Entangled systems can show correlations stronger than any ordinary local hidden instruction could explain. Measurement is not merely a passive glance at a pre-written classical fact, but part of the physical description of how outcomes become definite. That is the real change. Quantum mechanics did not say there is no reality. It said the old idea of reality was too simple. Classical realism imagined that objects possess definite properties at all times, whether or not anyone measures them. Quantum mechanics makes that view difficult to maintain at the smaller scales. Some properties appear to become definite only in relation to specific measurements. Some possible outcomes can interfere before one outcome is recorded. Some distant systems cannot be described as fully separate in the old intuitive way. And yet the everyday world remains real. Chairs do not vanish into probability clouds when no one is sitting on them. The moon does not need an audience to continue its orbit. A cup of tea does not enter a dramatic superposition of being both finished and not finished, although some evenings make that hard to judge. The familiar world is stable because quantum systems interact constantly with their environments. Decoherence helps explain why large objects lose visible quantum interference so quickly, and why ordinary reality appears definite, solid, and classical. So the difference is not between real and not real, it is between surface reality and deeper explanation. The surface world is the world of stable objects, shared measurements, chemical bonds, living cells, machines, planets, and stars. Beneath it is the quantum structure that makes those things possible. The solidity of matter depends on electron states, the Pauli exclusion principle, electromagnetic forces, and quantum chemistry. The light entering the eye arrives through photons. The electronics in modern devices depend on semiconductors, band structures, tunneling, and quantum behavior inside materials. The strange rules are not separate from ordinary reality. They are the reason ordinary reality can hold together. Even so, quantum mechanics is not a finished answer to every deep question. The measurement problem remains debated. Interpretations of quantum mechanics still disagree about what the wavefunction means and what exactly happens when a definite outcome appears. The challenge of unifying quantum mechanics with general relativity remains one of the great unfinished tasks in physics. Quantum field theory works extraordinarily well for particles and forces, while general relativity describes gravity and space-time with enormous success, but bringing them together completely has proved difficult. Research areas such as quantum field theory and curved space-time, string theory, loop quantum gravity, and black hole information all explore parts of this boundary. Black holes are especially important because they combine gravity, quantum theory, thermodynamics, and information in ways that remain only partly understood. These unresolved questions do not weaken quantum mechanics as a tested theory. They show that reality is still deeper than current understanding can fully reach. Quantum mechanics change reality by making it less obedient to human common sense. It replaced the dream of a fully visible microscopic clockwork with a theory of states, probabilities, measurements, and experimentally tested non-classical correlations. It showed that certainty has limits, that observation is physically meaningful, and that possibility is not merely ignorance, but part of the structure used to describe nature. Reality survived the change. It simply became stranger, sharper, and more precise. The universe did not dissolve into illusion. It revealed that beneath the calm surface of familiar things, the rules are quieter, deeper, and far less ordinary than anyone expected. So, quantum mechanics changed the meaning of reality because it showed that the physical world is not fully described by definite classical properties existing independently of measurement in the old intuitive sense. That is the careful answer. Not that reality is imaginary, not that the universe is a dream, not that particles need a human audience before they can get on with their day, which would be a rather demanding arrangement for everyone involved. The change is more precise, and in many ways more profound. Quantum mechanics showed that at the smallest scales, nature cannot always be understood as a collection of tiny objects carrying fixed properties along fixed paths, simply waiting for science to uncover them. Before quantum mechanics, the scientific picture of reality had a deep confidence to it. Newtonian mechanics made the universe look like a vast clockwork system, where matter moved according to laws that could be known, calculated, and trusted. If the position and motion of every particle were known, then in principle the future seemed predictable. The old dream of Pierre-Simon Laplace captured this beautifully. A perfect intelligence, knowing every detail of the present, could calculate all that had happened and all that would happen. Reality seemed difficult, but not fundamentally uncertain. James Clerk Maxwell added another layer to this classical world by unifying electricity, magnetism, and light through electromagnetic fields. Light became a wave moving through space, and the invisible forces around charged objects became part of an elegant mathematical structure. For a while, physics seemed almost complete. Matter moved, fields spread, heat flowed, light travelled. The universe looked as if it had given up most of its secrets, apart from a few stubborn details tucked away in laboratory corners. But those details mattered. Max Planck's work on blackbody radiation showed that energy could not always be treated as a smooth, continuous quantity. To make the observed radiation from hot objects fit the mathematics, Planck introduced the idea of energy quanta, tiny discrete packets of exchange. Then Albert Einstein pushed the idea further with the photoelectric effect, showing that light itself could behave as if it arrived in packets later called photons. Light, which had seemed so securely wave-like, now had a particle-like side as well. The atom deepened the mystery. Ernest Rutherford's gold foil experiment revealed the tiny dense nucleus at the centre of the atom, while Niels Bohr's model showed that electrons seemed able to occupy only certain allowed energy levels. The sharp spectral lines of hydrogen were not random colours. They were signs that atoms gained and lost energy in specific steps. Then Louis de Broglie extended wave-particle duality to matter itself, suggesting that electrons and other particles have wave-like properties. Matter was no longer simply little solid stuff. It had rhythm, wavelength, and interference hidden inside its behaviour. Erwin Schrodinger gave this strange world a new language through the wavefunction, and Max Born gave that wavefunction its probability interpretation. The wavefunction was not simply a physical ripple like water moving across a pond. It was a mathematical description of possible measurement outcomes. That was a major turning point. Physics could still predict with extraordinary precision, but what it predicted was no longer always a single definite path. It predicted probabilities, structured by precise rules. Werner Heisenberg then made the limit of classical knowledge unavoidable with the uncertainty principle. Certain pairs of properties, such as position and momentum, cannot both be perfectly definite at the same time. This is not because instruments are too crude, or because scientists are clumsy, or because electrons are especially private. It is built into the quantum description of nature. Wolfgang Pauli's exclusion principle added another essential quantum rule, showing why identical fermions such as electrons cannot all occupy the same quantum state, helping give atoms their structure and matter its stability. The double-slit experiment brought the strangeness into one of its clearest forms. A quantum object can behave as if multiple possibilities remain open before measurement, producing an interference pattern. Yet when path information is recorded, the interference disappears. Superposition showed that quantum systems can be described as combinations of possible states, while measurement raised the difficult question of how one definite outcome appears from a spread of possibilities. John von Neumann formalized the measurement chain, and the Copenhagen interpretation associated with Niels Bohr and Heisenberg placed measurement and experimental context at the heart of what physics could responsibly say. Then came entanglement, where two separated systems must sometimes be described together rather than as fully independent parts. Einstein, Podolsky, and Rosen used this to argue that quantum mechanics might be incomplete, because entanglement seemed to threaten the older idea of a local realism. John Bell later turned that debate into a testable theorem. Bell's theorem and the experiments of John Clauser, Alan Aspect, Anton Zeilinger, and later research groups showed that quantum predictions are not just philosophically strange, they're experimentally supported. Reality itself refused to fit the old combination of definite pre-existing properties and strictly local hidden instructions. Decoherence then helped explain why the everyday world looks ordinary despite all this, the work of H. Dieter Zeh and Wojciech Surek showed how interactions with the environment spread delicate quantum information outward, making visible interference disappear for large, warm, messy systems. A chair does not appear in an obvious superposition because it is constantly interacting with air, light, heat, and the surfaces around it. The ordinary world emerges not because quantum mechanics stops, but because it is working everywhere at once, too widely and too quickly for delicate possibilities to remain visibly separate. The interpretations of quantum mechanics show how deep the challenge remains. The Copenhagen interpretation, Many Worlds interpretation of Hugh Everett III, David Bohm's pilot wave theory, and objective collapse theories such as the Ghirardi-Rimini-Weber model all try to explain what the mathematics means. They do not all tell the same story. Some preserve collapse, some remove it, some restore definite particle positions, some suggest new physical processes. Quantum mechanics works with astonishing success, yet still resists one simple picture that makes everyone comfortable. And far from being only philosophical, quantum mechanics explains the structure of ordinary matter. Quantum chemistry shows why atoms bond, why molecules have shapes, why the periodic table exists, and why water, salt, diamond, graphite, proteins, and DNA behave as they do. Linus Pauling helped reveal how chemical bonding depends on quantum principles. Quantum tunneling helps explain nuclear fusion in stars and plays roles in semiconductor devices and some enzyme reactions. The theory that unsettled reality also explains why reality holds together. Modern technology rests on the same foundation. Semiconductors, transistors, lasers, magnetic resonance imaging, atomic clocks, solar cells, and quantum information science all depend on quantum mechanics. Bell Laboratories, John Bardeen, Walter Brattain, William Shockley, Charles Townes, Arthur Schawlow, Theodore Maiman, Isidore Rabi, Felix Bloch, Richard Feynman, David Deutsch, Peter Shaw, Love Grover, Charles Bennett, and Gilles Brassard all belong in different ways to the story of quantum ideas becoming practical tools. The same rules that seem to disturb common sense are reliable enough to build computers, hospitals, satellites, and global timing systems around them. So quantum mechanics is not a vague mystery, and it is not a license for magical thinking. It is one of the most precise and experimentally successful theories in the history of science. It changed reality most deeply by changing what physics can responsibly say about properties, possibilities, observation, information, and the limits of prediction. It showed that possibility is not always mere ignorance, that measurement is not always passive, and that information is part of how physical systems are described and controlled. The everyday world remains real, stable, and dependable. The floor stays beneath your feet. The moon keeps its quiet orbit. A warm cup stays warm for a while, then cools in the usual disappointing but thermodynamically respectable way. But the stability of that world comes from deeper quantum rules that are subtle rather than simple. Reality is not less real because of quantum mechanics. It is more layered, more delicate, more astonishing. The old clockwork universe was beautiful, but it was not the whole story. Beneath it lies a world of quantized energy, wavefunctions, uncertainty, superposition, entanglement, decoherence, and measurement. Not a fantasy world, but the real one, described more carefully than intuition ever managed alone. Quantum mechanics did not take reality away. It revealed that reality had always been stranger, quieter, and more finely woven than the classical imagination could see.